the treatment of equilibrium expressions. So we've already kind of gone over this in some earlier videos. Equilibrium expressions. Equilibrium, remember, is looking at how a reaction actually goes in real life. Equilibrium being that a ratio of products over reactants raised to the power of the coefficient. So if I have something like, see, CH4 gas plus O2 gas goes to CO2 and H2O. All this gases. I'm going to make this gases to make this easy on myself. Gas. Now, you want to think of this as being reversible, but technically every reaction is. Some of them to more extents than other. If I were to set up a K expression for this, K is equal to, so H2O squared CO2 over CH4 and O2 squared. The K would say when the reaction has stopped reacting, when it gets to the point where the reverse reaction is countered by the forward reaction and the forward and reverse are countering each other, what are the concentrations involved? Well, for this reaction, you would expect there to be almost none. So you would have a K that is exponentially large. These numbers would thus have to be very, very big. These numbers would have to be very, very small, depending on what was the limiting reactant. One of these numbers would almost be 0. Of course, it can't ever be fully 0 because we can't divide by 0. But you'd have a K that is incredibly large. Some reactions don't really happen. Some reactions don't really happen, and you could write an expression for that, where K would be really, really small. But one thing to note, when we write a K expression, we don't include solids or liquids. So if I say zinc carbonate plus what? Zinc carbonate goes to zinc oxide and CO2. Our K expression would just be CO2. So CO2 over 1. Meaning that the stability of zinc carbonate is really only controlled by the concentration of CO2. High CO2 means it's going to force it back to here. Low CO2 means it's going to force it the other way around. So we can look at these guys. But our K expression is just a understanding of how a reaction is going to go. We could look at a K as aqueous, or we can look at K as a pressure. K as a pressure. We can exchange the two based on the following reaction. You're going to say, if concentration is moles over volume, how do you turn moles over volumes into a pressure? Well, you're going to use RT. PV equals nRT. So you're going to times your Kc by your RT, and that's how you're going to get your Kp. So every time you see a concentration, you're going to multiply by RT. So in this equation, you have RT, RT, RT over RT, RT, RT. So looking at that, 3 RTs on top, 3 RTs on bottom, they cancel out. 3 RTs on top, 3 RTs on bottom, they cancel out. But this one, there's only one thing. So you'd multiply RT right there. And so to get Kc into Kp, you would just multiply every gas by RT. So they often give the expressions Kp equals Kc times RT delta N. Delta N is the change in moles. This one has 3 moles on the right. This one has 3 moles on the left. So how many change in moles? The change in moles are 0. This one, it has 1 mole on the right, 1 mole of gas on the right, 0 moles of gases on the left. So the change is +1. Building on that, there's one other big thing we look at. We look at the idea of Q. Q has a relationship to K in that Q is set up exactly the same as K. Q is products over reactants. Products over reactants raised to the power of their coefficients. So like, let's see. I'm trying to think of a reaction. Now let's say NO2, 2 NO2s goes to N2O4. N2O4. So our Q expression would be N2O4 over NO2 squared. The only difference is that Q, by definition, does not have to be at equilibrium. K is always looking at when the reaction has ceased. But Q could be at any point of the reaction. It's just like taking a quick, checking your GPS and seeing how close we are to the location. While K is always, we are there at the destination. So depending on the concentrations of N2O4 and NO2 during that snapshot, we can figure out how close we are to the destination, how close we are to equilibrium. If Q is greater than K, Q is greater than K, it means we have, in this case, too much N2O4. How would you decrease that? You would say N2O4 goes down. This guy has to decrease, and then NO2 would go up. And that would bring it back to the K. If Q is less than K, it means too much reactants, too much NO2. And so this guy would have to go down, and N2O4 would go up. And so we could, by looking at Q, we could figure out how close we are actually to equilibrium. And one other thing we could deal with when we dealt with equilibrium was that Le Chatelier's principle. Le Chatelier simply said that by changing various aspects, we could disturb the QK expression, and force it towards one side or the other. Remember, there's K only changes with temperature, So the only way to actually change K is by increasing or decreasing the temperature. All other things would just disturb the Q. Le Chatelier said we take from Q equals K to a situation where Q does not equal K, and so it has to shift to get back. Shifts to get back to where Q equals K. It doesn't matter how you do it. If we remove a product, Q is then less than K, and so it goes to the right. If we remove a product, it goes to the right to replace the product. If we remove a reactant, Q is greater than K, and so it has to shift to the left to replace the reactant. If we add a reactant, Q is greater than K. Less than K, and so it has to shift to the left. If we add a product, Q is greater than K, and it has to shift back to the left. It shifts to replace the removal. It shifts away to remove the addition. We could also treat it with pressure, but changing the pressure does not Change in pressure just changes concentration. And pressure changes concentration. Because pressure is equal to nRT over V. The moles aren't going to change, but the volume will when the pressure goes up. So when we change pressure, when pressure goes up, we move to less gas. Less gas. If we decrease the pressure, it goes to more gas. The only way to change our K is when we look at change the temperature. Change in temperature changes K. K, so Q no longer equals K, and it has to shift. If it's exothermic, that means heat is a product. Increase in T means it's going to shift to reactants. Shifts left. Decrease in T would mean it shifts right. We're trying to replace whatever we removed. If it's endothermic, heat is a reactant. Increase in T would be shifting away from the addition. Decrease in T would be shifting towards the subtraction.